Everybody has experienced the outward sensation of being on a rotating body. This outward sensation is really a manifestation of an inward force called the centripetal force, which we will examine in this video entitled Centripetal Force Experiment by William Benzing. In this presentation, a comparison is made between experimentally derived and theoretically derived values of the centripetal force. This force is an inwardly directed force that causes a mass to move in circular motion like the moon around the earth due to the gravitational force. This diagram shows an object with mass m rotating counterclockwise at an angular velocity omega. The inwardly directed centripetal force, F sub c, shown in red, acts along the circular radius r. If this force were to vanish, the object would fly off in a straight line at linear velocity v, shown in blue. The classical equation for centripetal force is shown at the right. The centripetal force is equal to the mass of the object times the linear velocity squared divided by the turning radius r. Due to difficulty measuring the linear velocity, this equation is modified for experimental simplicity. In circular motion, the linear velocity v can be calculated by multiplying the turning radius r times the angular velocity omega. Substituting r omega for v and simplifying, the centripetal force equation becomes mass times turning radius times angular velocity squared. The angular velocity can then be easily calculated by counting the time for a given number of rotations. To experimentally verify the theoretical equation, the apparatus shown here was constructed using two tennis balls tied together with nylon fishing line, which runs through a PVC pipe. There's a light ball on top and a heavy ball on the bottom. The upper tennis ball is empty with a mass of 0.004 slugs, and the lower tennis ball is full of sand with a weight of 0.45 pounds. When the pipe is rotated faster and faster, the lighter ball moves outward till the heavy ball is just below the PVC pipe. When this occurs, the lighter ball moves in uniform circular motion with a constant turning radius of 2 feet and a known centripetal force equal to the weight of the heavy ball, namely 0.45 pounds. The angular velocity omega was calculated by timing 10 complete revolutions to get revolutions per minute and then converted to radians per second. The following videos show 4 attempts to collect experimental data with this apparatus. Attempt number 1 was a failed attempt and shows the dangers of experimental physics. However, attempts 2, 3, and 4 were successful and provided good data with which to calculate the experimental centripetal force based on the equation. This is attempt number 1. Okay, there. Ouch! Science can be dangerous. This is attempt number 2. Okay, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, stop.
8.35.
All right, that's good. This is attempt number 3.
Okay.
Go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
8.36.
And this is attempt number 4. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop.
8.40.
The experimental data for trials 2, 3, and 4 are tabulated in this table. The columns are labeled left to right. The first column is the attempt number, next in the turning radius in feet, the angular velocity in revolutions per minute, and radians per second, the linear velocity in feet per second, mass in slugs, and the calculated and known centripetal forces in pounds. Finally, the last column shows the percent error between the two forces, the known and the calculated centripetal force. In all 3 trials, trials 2, 3, and 4, the differences between the two forces are less than 1%. Consider attempt number 3. And in attempt number 3, the known centripetal force is 0.450 pounds, and the calculated was 0.452. And that results in an error less than 1%. I believe it's 0.4%. But in every case, the difference between these two forces, the theoretical and the known, is less than 1%. In conclusion, there is good agreement between the experimental and calculated centripetal force in circular motion. Thank you for watching.